Homographies in UAV imagery can estimate relative positions for multiple UAVs, which is important for GPS-denied scenarios. Our research presents a reliable and fast algorithm for homography estimation. There are a few limitations with current homography estimation methods. The two most common approaches are direct methods and feature-based methods like SIFT. These methods struggle with large illumination changes. They can also fail when images have low texture. Finally, they can fail when the images have significant noise. In these examples, red represents the ground truth correspondences and yellow the estimated correspondences. Our algorithm is not as susceptible to these problems. The standard deep learning-based end-to-end approach for homography estimation consists of the following steps. First, the two input images are cropped and stacked to obtain patches that are fed into a CNN-based regression network. This network then outputs a 4-point parameterization of the homography, which is then converted into the standard 3x3 matrix representation. A supervised approach uses a ground truth label to produce an L2 loss signal to train the network. However, homography ground truth is not easy to obtain in the real world, thus limiting this approach mostly to synthetic datasets. Our unsupervised approach, on the other hand, requires no ground truth, making it more suitable for robotics applications. First, we convert the 4-point output of the regression network into a 3x3 matrix representation. We then warp the first patch and compare against the second patch to obtain a photometric loss to train the network. This procedure, however, encompasses a couple of challenges. First, the mapping between the two homography representations has to be differentiable. To solve that, we use the direct linear method on tensors. Second, the warping of the first patch has to also be differentiable. To solve that, we make use of the spatial transformer layer. Finally, the model has to cope with illumination changes, so we perform data standardization augmentation. In addition, we use the L1 loss function, which empirically we found to perform better than the L2 loss. The intended application on robots motivates us to quantify the trade-off between speed versus accuracy. As can be seen in the figure, our approach, shown in purple, outperforms other methods when considering both metrics, making it appealing for robotics. Here are some more examples showing our superior performance versus the traditional methods in an aerial image dataset. However, our approach can still fail, usually when the first image is significantly darker than the second image. A potential solution could be to apply a left-right consistency in the loss function. Thank you.